send packets from one VLAN to another. There are several methods of performing inter-VLAN routing. The one that you guys are going to be tested on is routing on a stick, which we'll take a look at. And I'm going to actually kind of go through the process of how that inter-VLAN routing process works. But before we get there, let's just talk about, in general, what inter-VLAN routing is. And really, it's just one definition. The ability to take packets from one VLAN and route them to another VLAN. Inter-VLAN routing. I know it's shocking, right? So there are essentially three ways to do inter-VLAN routing. There's a traditional way, which is depicted on this particular diagram here, where you have essentially a separate router interface per VLAN. Not very scalable, but certainly effective. Then you have something called router on a stick, where you're essentially routing multiple VLANs over a single interface. And then lastly, you have multi-layer switching, which gives you the ability to route traffic through the use of something called SVIs, or switched virtual interfaces. Okay? So we've got several different ways. We'll look at the configuration of each of these methods. We'll talk about the pros and cons for each, when you would want to use one versus the other, and then we'll just wrap up this chapter. It's not a very long chapter, and believe it or not, we did actually cover about 100 slides before lunchtime this morning, so we were making good progress. We just have about 100 left to go, maybe a little bit more than that. All right. But a lot of very short chapters to go. I mean, spanning tree is kind of a long chapter, but that's a fun topic to talk about. Okay? And if we do access lists first thing in the morning, it's not going to be a big deal. And here's the reason why. Because access lists are covered on the security portion as well as CCNA. So if we do have to push anything to the morning, that's probably the one section we'll push over to the morning. All right, legacy inter-VLAN routing. Like I said, that's where you would have a router that has multiple physical ports or physical interfaces, and each VLAN would be connected to a different physical router interface. What do you guys see as the potential problem with this particular method of moving traffic from one VLAN to another? Expensive. I thought you were giving me a hint.
Oh. Yeah, I'll take some.
It's expensive, right? It's expensive in the form of real estate, but it's also expensive in the form of, actual physical property, right? I mean, because how many organizations have a small number of VLANs? Most organizations are going to have a large number of VLANs in their enterprise, and to say that we're only going to have a couple of interfaces that allow us to communicate from one VLAN to another is not really that practical. I mean, even if you just extrapolate it a little bit and say we're going to have 10 VLANs, that's 10 router interfaces. And routers are notorious for not having a whole lot of interfaces. You follow what I'm saying? Now, the benefit certainly is that it's relatively easy to configure. We don't need any trunk ports. There aren't going to be necessarily any bottlenecks as far as utilizing an interface more than once to send or receive traffic, but it doesn't really scale well. Large networks, not even large networks. I mean, we have customers with 50 or 60 people, and they're running 10 or 15 different VLANs or 20 different VLANs. That's not uncommon because of the types of traffic that they have. Of course, we know that the most efficient way to do inter-VLAN routing is on a multi-layer switch. So with regard to inter-VLAN routing, well, I'm not even going to talk about that slide. Let's just take a look at what it looks like here. All right? You got a PC over here in VLAN 10, wants to talk to a PC in VLAN 30. All right? Now, again, the PCs don't really know that they're a member of a VLAN. It's the switch port that's a member of a VLAN. So we have VLAN 10 and VLAN 30 on each of those respective ports. What happens when the traffic hits port 11? It gets tagged into VLAN 10, right? We'll just put a little 10 here, as a matter of fact. We tag that traffic into VLAN 10. Make sure these guys online can still hear me. Can you guys hear me? All right. Okay, great. Is port 4 a trunk? Remember what I told you about the rule. Is port 4 a trunk? When do we use a trunk? When we have to pass traffic for more than one VLAN. Does port 4 have to pass traffic for more than one VLAN? The answer is no.
Okay, 30.
Well, take a look at the diagram. Port 4 is only in VLAN 10, right?
Right.
So this tag actually gets removed before the traffic goes up to the router. So the tag gets imposed here, it gets removed here. This router has two connected interfaces, one in VLAN 10, one in VLAN 30, or one in subnet 10 and one in subnet 30. So the router does its normal internal routing, sends the traffic down this network. What happens when the traffic enters port 5?
Okay. No, it doesn't.
It gets tagged
In the ingress?
on the ingress, but in this case, it's going to get tagged into VLAN 30, right? And of course, when it leaves the switch, the tag's going to get removed and sent over to the PC. Does that make sense? I'm actually a little surprised that a few of you didn't follow that, but does it make sense now? We don't have any trunks in this particular diagram. And the reason we don't have any trunks is because we don't have any interfaces passing traffic for more than one VLAN. It is easy, right? It is easy because all you have to do is configure the VLANs and assign them to the interfaces. You just have to put IP addresses on the router interfaces and turn them on. You thought the router on a stick with the trunk between switch and router. No need for that in this case, because these links are there to serve those two VLANs, right?
And a physical interface for the router.
Right. Now, you had VLAN 20, you had VLAN 50, you had VLAN 100, all of a sudden this doesn't look so good. Because now that router, which it's not uncommon for routers to have two interfaces, but now that router has to have 5 or 6 or 7 interfaces. So what are your configuration tasks for the switch? We just talked about this right before lunch, right? What are the configuration tasks on the switch? Anybody?
Creating VLANs.
Create the VLANs,
Assign the interface.
assign the VLANs to the interfaces. That's right. All right? Who's giving you advice? And on the router, all you do is turn on the interfaces and then put IP addresses on the interfaces. You don't even have to use a routing protocol, right? There's no need to use a routing protocol here because there's no other router to talk to. So this is what the configuration looks like. Go into the switch, VLAN 10, VLAN 30, interface VLAN are on port 11, assign that to VLAN 10, port 4, assign that to VLAN 10. Port 4 was the one that goes to the router. Port 6 assigned that to VLAN 30. Port 5 assigned that to VLAN 30. Port 5 is the one that goes to the router. That's it for the switch. And then on the router side, you just put an IP address on the interface and turn on. Okay? Then you're completely done. The clients get a default gateway of the router interface. They get an address within their subnet. Hunky-dory. Okay? Now, the method that you guys are tested on, and you guys are going to have to go through these questions tonight because there's a study section in the review called Router on a Stick, is routing on a stick. I'm not sure why Cisco tends to focus their attention on this method because it's really not the most common method of routing between VLANs, but nonetheless, that's what they test on. All right? Router on a stick solves one problem. What is that?
Needing an interface for each VLAN.
Needing a separate interface for each VLAN. But it creates another problem, which is what? A bottleneck. Because instead of having a separate interface for each VLAN, we create a trunk that goes to the router, and we route multiple VLANs over one interface. That doesn't work as well if you have lots and lots of VLANs. So there's a plus and a minus. Now, the question that I always get with this particular design model is, how many VLANs can I support? Is it really a limitation of the VLANs, or is it simply a limitation of the amount of traffic? I mean, technically, if you only have a couple of hosts per VLAN, you should be able to get away with a lot more VLANs, right? As opposed to if you have 1,000 hosts per VLAN, then you don't get to have as many VLANs. So it's not really a function of the number of VLANs, it's really a function of the density of hosts within the VLAN. Does that make sense? All right. There is kind of a solution to that, and I'll talk about that in a second. But in this particular case, one physical router interface is configured for tagging. I want to make that distinction. Routers do not understand trunking. And in fact, they don't even care about trunks. They don't care about VLANs at all. But there is a reason why the router does have to understand tagging. We'll see a diagram, and I'll go through the scenario like we did with the first method. I'll go through the scenario of sending traffic up to the port and back down and so on. The way that we facilitate communication of multiple VLANs on one physical port is that we divide the physical port into something called subinterfaces. It's interesting because you can come into a device. Let me pull one up. You can come into a device and you can actually create a large number of subinterfaces on a physical port. I'm not sure why this is the case. Every time I see this, it reminds me of something. Let me pull something up. I want to show you guys something. I have a bunch of these left. I might have to share.
You should write a book.
Huh?
You should write a book for all this stuff.
You should write a book.
You should write a book
Yeah.
for all this stuff.
Yeah, I thought about writing a book.
Your memoir for your mind age.
I thought about writing like a CCNA book, but because I know Todd Lamley.
Mm-hmm.
He's kind of a jerk. And everybody buys his book.
Okay.
Who, Todd Lamley?
No.
Oh. don't know if he's gay or not.
No, it's on the corner of the picture of Blake Shelton trying to kiss a guy.
Oh, well, you know, that's because that's what I search on. That's a cookie on my laptop. Like Sheldon kissing. No, there was a photo that I wanted to show you guys. You guys can appreciate this, I think, more than most. I mean, if I can find it. Timeline photos, it's probably got to be under here. Yeah. This is a shirt that we produced that we usually give out to people. Everybody gets a kick out of that. Every time I see that, I think of that shirt. Used to give them out in every class, but I don't know where to stop. But, yeah. Nice geeky shirt that a Cisco person would wear. All right, hey, I digress. Yeah.
Oh, that's something unique.
Yeah, in case you guys didn't see that, it was a naked router. All right.
It's free BFE. That's old.
I know a guy that had the Linux penguin tattooed on.
I want the Linux penguin, he's screwing no, it's a free BFE screwing the Linux penguin. That's what it was. The devil behind the penguin, you see that one?
I haven't seen
He's
that.
got the penguin bent over. But I thought, nah, I got kids, that won't work.
You know, just say they're doing exercises. All right.
Well, I wasn't gonna put a window logo on that.
Interface. This is how you create a sub-interface, by the way. I know what you mean, Giovanni. You sly Italian. All right, interface,
Paisano.
GI, 0/0, or whatever. It doesn't have to be a gigabit interface. It doesn't have to be Ethernet. It can be serial. You put a dot, and then you specify a number. And this is how many sub-interfaces you can create. Why you can create 4 billion sub-interfaces, I have no idea. But for some reason, they chose that number. Right?
And why do you need more sub-interfaces than there are VLANs?
Yeah, exactly. If you have a router with 4 billion sub-interfaces, you probably have other problems. You have 99 problems and your router is 1, all right? So, dot 1 creates sub-interface, right? Dot 2 creates a sub-interface. This device doesn't have gig, but you get the idea, all right? So you can
Well, it
have,
says gigabit interface.
yeah, I don't know why it's giving me
What the
that
hell?
error.
That's weird.
GI 0/0. That is weird. Why is he yelling at me about that?
Did the question mark after the period?
Yes, of course. That's how I showed you to. Oh, see, it doesn't do gig.
That's kind of dumb.
That is really lame. See, this is another bug in Packet Tracer. I don't have any gig interfaces, but it lets me put in a gig interface.
Can you do one without the straight gig interface?
You can do one for fast Ethernet, yeah.
No, I meant,
Is it because the iOS knows the command that the router doesn't actually have, but you're not actually
Pretty
executing
much,
from it,
yeah.
you're just
Just another
asking about
bug.
it?
Yeah, just another bug.
yeah.
But each time you create one of these sub-interfaces, they're just going to show up as regular interfaces. Do you show up the interface brief? They just show up as regular interfaces. Okay? All right? They're all tied to this physical port, but they're logical interfaces. We create sub-interfaces for all kinds of things. On serial interfaces, we'll use sub-interfaces so that we can split frame relay connections, like point-to-point versus point-to-multipoint. And we'll use sub-interfaces in Ethernet to do things like trunking, all right, or separating VLANs. So there really is no physical limitation at least from a router's perspective, on the number of sub-interfaces you create, that's practically a limit. The limit is going to be either the number of VLANs, or it's going to be the amount of traffic you're trying to shove over that interface. All right? So from a scalability perspective, outside of the limitation of the amount of traffic you're trying to route, there really isn't a limitation, because you can clearly create more sub-interfaces than you have VLANs. All right? Now, there is a very specific configuration process that you have to follow in order to configure each sub-interface with an IP address. I'm going to show you that in a little bit. The gateway for the clients is simply the IP address of the sub-interface for that respective VLAN. In this case, it says here only one router's physical interface is used. You can actually use more than one router interface for this process. You can actually use multiple router interfaces for this process. But you can also only use one if you want to. You're not required to use more than one. What would be the benefit of using more than one physical interface? So say VLANs 1 through 20 are on Fast Ethernet 01, and VLANs 30 through 50 are on Fast Ethernet 00.
Load balance.
Load sharing, right? Giving you the ability to have kind of more traffic, even though you have twice as many VLANs. I cannot think of a scenario where I've actually, outside of a lab environment, where I've actually implemented this as a production option. Right? In most cases, I'm using multi-layer switching to do my inter-VLAN routing. What is the latest and greatest technology that exists today that gives us the ability to perform high-speed routing between VLANs over multiple devices? Multi-layer switching, but in combination with stacking, switch stacking. Like the 3750s, the 3850s, where you can have stacked cables between them, because that stack cable operates at 32 gigs a second. If you don't have to physically leave the device over a 1 gig connection, that's much better. All right? So, the preparation tasks, well, we'll see it. Let's just take a look at the configuration here. Same concept that we talked about before, but let's take a look at the process of where tagging occurs, where it doesn't occur. Traffic comes up to port 11. Traffic gets tagged into VLAN 10. Is the tag removed, or does the tag remain over port 5?
Stay, right? That's going on a trunk.
It's a trunk, right? So unless it's the native VLAN, the tag is going to stay on. You follow me? So the tag, traffic comes up here tagged. Does the router really care whether or not the traffic is tagged? The answer is no, because what layer is tagging occur at? Layer 2. What is the only thing that the router is concerned with at layer 2?
Source and destination MAC.
Destination MAC, actually, not the source. It wants to know that the MAC address of the frame is for the router. And by the way, sub-interfaces don't have a separate MAC address per interface. We still use the same single MAC address because it is the same physical port, isn't it? So the frame comes into the router tag. The router looks at the destination MAC and says, oh, that's my MAC, yay. Strips off layer 2. Does a routing table look up and says, oh, that traffic needs to go out of Fast Ethernet 030. Dang it. That traffic needs to go out of Fast Ethernet 030. 00.30. What does the router have to do with the packet before it sends it back to the switch? What does any router have to do with a packet before it sends it back out? Come on, guys, you know this. You got 10 seconds, I'm walking out of here.
You retag it.
It has to re-encapsulate the data, doesn't it? Because remember, layer 2 is stripped off. Layer 2 needs to be added back on before we send the data back down the switch. But in this particular case, the switch expects to receive what type of frame? What type of frame does the switch expect to receive?
Tag.
A tagged frame. But in this case, it's tagged in VLAN 30. So the frame is actually re-tagged by the router. So even though the router doesn't care about tags, it has to recreate a tag because the device that it's sending the traffic to expects to see a tagged frame. You follow me? A lot of people call these links to the routers trunks, and from the switch's perspective, they are a trunk. But from the router's perspective, they're not a trunk. Routers do tagging, but they don't do trunking. It's kind of a weird concept, but routers don't really do trunking. Not in a traditional sense. Of course, when that traffic leaves the interface, what happens to the tag? It gets removed, and we go back down here untagged. So from the switch's perspective, this is on the task. What are our configuration tasks? We need to set port 5 up as a trunk, right? Switch port mode trunk, switch port mode negotiate. I'm going to ask you guys something. I was thinking about this during the break, and I had forgotten to bring this up because you guys will see this in, undoubtedly at some point in your career you'll see this. So let me just show you real quick. If you go onto the CCNP, you'll definitely see this. Anybody have plans to do their CCNP? Maybe you're getting redo yours, right, Mr.
If I can convince my employer they need a CCNP.
Yep. Invest in yourself, my friend, and then look for a new employer. If they don't think you need a CCNP, find an employer that does. Right? I noticed you guys did raise your hand.
Eventually.
Yeah. Okay. Config T, interface FA01. Switch port mode trunk. Uh-oh. Command rejected. I picked this particular switch model for a reason. Switch port trunk encapsulation. This is a command that we did not see in the VLAN lecture. And I was thinking about it before lunch, and then I don't know, I was thinking about it during lunch, and I was like, you know what, I didn't talk about that command. There are certain switches that run multiple tagging methods. Now, it's interesting that Packet Tracer only shows you one, but they require that you set it anyway. This command is required. Normally, it would be ISL or .1Q. So if you try to set an interface as a trunk and it gives you this error, an interface whose trunk encapsulation is auto cannot be configured in trunk mode, you basically need to set the trunking mode manually. Like I said, it's either going to be ISL or .1Q. In this case, it's .1Q. And then I can do the switch port mode trunk. All right? I don't know why I thought about that just then, but
What model switch is that emulating?
that is a 3650. But actually, even the 3700s require that. It's not reserved for older switches. For some reason, and I'm not sure why, because the 3700s run XE software, but for some reason, certain switches have ISL built into them as well.
The X series stuff. Is set now. Oh,
3750s and 3750Xs. Yeah. By the way, I love those 3750 switches. You can get them on eBay now for about $100.
they're nice switches.
They're very good switches. They used to cost several $1,000s. Then Cisco made, I remember back in the day when Cisco didn't used to put out stuff every quarter. But I guess they got smart and decided that they could make more money if they kept bringing up all these revisions. So, all right.
2960s only, they only support .1Q, right?
Right. There are, most of Cisco's switches only do .1Q. But for some reason, some of their switches have ISL on them too.
But isn't that weird though, because ISO was a Cisco
ISL is Cisco proprietary.
which is kind of weird.
Why did ISL kind of go away? Well, how much overhead does .1Q tagging add to a frame? You guys should know this, we just talked about it.
4 bytes.
4 bytes. 4 bytes of overhead. ISL adds 20 bytes of overhead.
Should wait for $100 off.
Yeah, I just spent that. ISL adds 20 bytes of overhead for an 18-byte header. That's a little ridiculous.
That's Cisco.
More than doubles. Hey, they came up with the concept of VLANs, so you got to give them something. Al Gore was working for them for a while. And they invented the internet.
Is that when he invented the internet?
Yeah.
That's it.
That's what's going to be on his tombstone. He invented the internet. You guys know all these commands: switchport mode trunk, switchport mode negotiate. Optional, right? No negotiate's an optional command. What did that command do? Disables DTP. Switchport trunk allowed VLAN 1030, also an optional command. That's called pruning. Basically locking down our trunk to only support certain VLANs. Even if you prune off VLAN 1, we had a question about this during lunch, I think you guys are already gone. Even if you prune off VLAN 1, it's still there. VLAN 1 can never be removed from a trunk. And that's because CDP, spanning tree, all the other switch-to-switch protocols use VLAN 1. On the router side, now this is new. You haven't seen this before, unless you've done routing on a stick. Pick a sub-interface number. Test question, the sub-interface number does not have to match the VLAN. Logically, it makes sense to make the sub-interface number match the VLAN, but it does not have to match the VLAN. This command, though, does have to match the VLAN, because this is the command that describes how frames should be tagged when they leave this interface. In this case, tagged in VLAN 10. It makes sense to go ahead and make these match. Why not? You have 4 billion sub-interfaces to choose from. You might as well create a sub-interface number that matches the VLAN.
Get less confusing.
Yeah, absolutely. You need more VLANs, you can create more sub-interfaces. All right? The last thing, and don't forget this, you have to turn on the physical port. You don't do a no-shut on the logical ports. You do a no-shut on the physical ports. And that's what brings up those logical ports. Not that complicated, pretty simple. There are some verification steps that we can do. Certainly show IP route. Notice that each of the connected subnets are now tied to a respective subinterface. Does that mean I need a routing protocol? Do I need a routing protocol to route from one VLAN to another? The answer is no. They're connected routes, right? That's also on the test, by the way. And we're just hitting all kinds of test questions now. The only time you need a routing protocol is if you're talking from one router to another. In this case, we don't have two routers. We only have one router. You can also do show interface trunk. You can see that VLANs 10 and 30 are allowed across the trunk. Port 5 is a trunk. The mode is on, meaning that we set the trunk, hard set the port to a trunk. And the encapsulation on the trunk interface is 802.1q. If you do a show interface, you'll see that you have encapsulation running on the interface. Okay. Questions? Not so far? Great. The last step, and practically speaking, the most common method of inter-VLAN routing is to use a multi-layer switch. Perfect example. Let me pull up a customer diagram here. See? Let's see. This will work. Very small network for one of our customers. Physical redundancy in the form of these stackable devices here. But essentially, this is the core switch in the network here. It's a stack, right? We've got 1, 2, 3, 4, 5, 6 switches in a stack. And what we have is, yes, I'm very particular about my network diagrams. They're artistic. We have I think we have probably, let me see here. 1, 2, 3, 4, 5, 6, 7, 8, about 9 VLANs, 10 VLANs, right? On this switch. Here's how it works. You go into the switch, interface VLAN 10, give it an IP address, 10.10.10.1, no shut. Interface VLAN 20, IP address 20.20.20.1, 255.255.255.0, no shut. Sorry about that. And you execute the command IP routing. This is the command that makes a multi-layer switch a multi-layer switch. If you can execute this command, you have a multi-layer switch. Because what you're doing is you're enabling routing on that device. All that means is that there's a route processor built into the device. So let's say in our topology here, I have a client down here connected to VLAN 10, and I have another client connected to VLAN 20. The traffic will go up to the core switch. It'll get switched between the SVIs, and then it'll come back down. If you've got a bunch of, this is 6 switches here, so we've got a bunch of ports here, right? Then all of a sudden, you don't even have to leave the device. Now you're doing switching at wire speed, or routing at wire speed, right? So that's kind of a modern design now, where you have this device that's doing all the routing internally. All right? SVIs are seen as layer 3 interfaces. We configured an SVI on day 1. Man, that seems like such a long time ago now, doesn't it? Day 1, 4 days ago. Well, we created an SVI for management. We didn't create one for routing. The only difference between a routed SVI for routing and an SVI for management is the execution of the IP routing command. This is an extremely scalable solution because for a customer that has maybe 500 users, they can get a stack of switches. They can get a stack of switches, 3750Xs or 3850Xs. They can connect those switches with the stacking cable, right? Create SVI 1 through 20 on the core, and then every client connected to this stack never leaves the stack to route from one client to the next. So you have essentially a limitless amount of bandwidth to get from one client to the other. Certainly much faster than if you left the device on a wire. I mean, practically what's the fastest speed you're going to get on a wire in Ethernet? Practically, what's the fastest speed you're going to get on a wire in Ethernet? Gig. From a client perspective, practically speaking. Now, there is 10 gig Ethernet over copper, but it's not practical for your end users. All right? So we have these SPIs. The switches that do this, let me pull up a pretty picture, because there are some other switches that do this as well. You guys have probably heard of the Cisco 6500s. Right? These switches here. Massive density, massive port density. You've got 13 blade options, you've got 9 blade options, 7 blade options. So you can fill up this chassis with a whole bunch of gigabit Ethernet ports. Your route processors go in here. This is one big network in a box. All right? You got your redundant power supplies, you have redundant fan trays that are connected, all kinds of wonderful things. That's why multi-layer switching tends to be the most common method of routing between VLANs. So traffic flows from one VLAN to another. The tagging still occurs, by the way. It just occurs internally. The tag gets imposed on the port where the client is connected. When we go from one SVI to another, the tag gets deposed, and then the tag gets reimposed for whatever VLAN that we're going to. So VLAN 10, VLAN 30, interface VLAN 10, IP address, interface VLAN 30, IP address, IP routing, you're done. Okay? And we're done with that chapter.